The future of fusion energy, unlocking the power of the stars. Introduction. Fusion energy has long been considered the holy grail of clean energy, a virtually limitless, safe, and sustainable source of power. Unlike nuclear fission, which splits atoms and creates long-lived radioactive waste, fusion merges light atomic nuclei, usually isotopes of hydrogen, to release massive amounts of energy, just like the sun does. For decades, scientists have tried to replicate this process on Earth. Now, with recent breakthroughs and global investments, we are closer than ever to making fusion a reality. 1. The science of fusion. At its core, nuclear fusion combines two light nuclei, usually deuterium and tritium, isotopes of hydrogen, into a single heavier nucleus, releasing energy due to the mass-to-energy conversion, as per Einstein's equation, E mc2, fusion reaction. Example, deuterium 2H plus tritium 3H, helium 4He, plus neutron plus 17.6 MeV of energy. This energy is carried by fast-moving particles, which can be harvested to generate electricity. 2. Why fusion is so promising. Abundant fuel. Deuterium can be extracted from seawater, and tritium can be bred from lithium. No greenhouse gases. Unlike fossil fuels, fusion emits no CO2. Minimal radioactive waste. It produces much less long-lived radioactive material than fission. Inherently safe. No chain reactions. Any malfunction would simply shut down the reaction. 3. Major fusion approaches. Amagnetic confinement, e.g. tokamaks. Example, ITER, International Thermonuclear Experimental Reactor in France, uses powerful magnetic fields to confine hot plasma over 100 million degrees C in a donut-shaped device. Climb achieve more energy output than input, net energy gain. B. Inertial confinement, e.g. laser fusion. Example, National Ignition Facility, NIF, in the USA, uses powerful lasers to compress and heat fuel pellets until fusion occurs. In 2022 and 2023, NIF achieved ignition, a milestone where the energy out exceeds energy in to the pellet. C. Alternative startups and approaches. Compact fusion reactors by companies like Commonwealth Fusion Systems, TAE Technologies, and Helion Energy are exploring innovative, cost-effective designs. 4. Recent breakthroughs. 21Jet, UK, set a record for sustained energy output. 2022-2023. NIF achieved net energy gain in a fusion reaction, a major scientific milestone. 2024-2025. Helion Energy announced plans to deliver fusion power commercially by 2028, backed by companies like Microsoft. 5. Challenges ahead. Sustained energy gain. Achieving continuous net energy gain remains a hurdle. Materials. Plasma-facing components must withstand extreme heat and radiation. Cost and complexity. Building and maintaining reactors is still very expensive. Tritium supply. Tritium is scarce and needs to be bred efficiently in reactors. 6. Global fusion projects. ITER, France. The 25B international mega-project with 35 nations aims for first plasma by 2025-2026. Spark, USA, a compact high-field tokamak developed by MIT and Commonwealth Fusion. K-Star, South Korea, achieved over 30 seconds of sustained plasma at 100 million degrees C. China's East, sometimes called the artificial sun, it achieved over 1,000 seconds of sustained fusion. 7. The path forward. The fusion community envisions a fusion pilot plant in the 2030s, with commercial reactors likely by the 2040s. While it's not an overnight solution to the climate crisis, it could provide clean baseload energy for centuries once viable. Governments and private sectors are now collaborating more than ever, with a wave of fusion startups attracting billions in investment. This signals a new era where fusion is no longer just science fiction. Conclusion. Fusion energy holds immense potential to reshape the global energy landscape. With sustained funding, political support, and international collaboration, humanity is on the brink of replicating the power of the stars, offering a cleaner, safer, and more sustainable energy future.